Hi everyone, I'm Babak, and today I'll be presenting our paper titled "Less is More," which is about quantifying the security benefits of debloating web applications. This is a joint work with my colleague Pierre Laperdry and my advisor Nick Nikiforakis. So to begin, let us define what is the meaning of software debloating. So software debloating is the act of removing pieces of code from a target application, and these are the pieces of code that the users are not going to be using, and our goal is to reduce the attack surface of these applications. So as a motivating example, we can take a look at this web cache poisoning vulnerability affecting Drupal and other popular PHP frameworks. So to understand this vulnerability, first we have to know that IIS used to support specific HTTP headers, specifically X original URL and X read-write URL. And the way these headers work is that, so in this example, you have a GET request to /education, but X original URL points to /gambling. So now if the web server or the web application is aware of these headers, they will respond with the content of /gambling. Now, if there is a web cache sitting in front of the application that is not aware of this header, it becomes troublesome, because the web cache will take /education as a key for this cache, but the content of /gambling is cached here. So any subsequent request to this page by other users will load the content of /gambling. And this can obviously be used to mount different types of attacks. Once this vulnerability was reported to Drupal, they realized that they don't have any direct reference to this in their source code. And the support for this header is coming from Symfony, which is a popular PHP framework that we're using. So they notified Symfony, and Symfony also reported that they borrowed this piece of code from Zend framework. So you see the pattern here. We have a feature that is very rarely used, and this is coming down the chain of external dependencies, making your application vulnerable. So we're hoping that debloating can target such vulnerabilities. So to understand that and to quantify that, we came up with this pipeline, which I'm going to describe. So in the first step, we find a large number of CVEs for target applications, and we map them to the source code of our target application so that we know specifically which parts of each application relates to which CVE. And later on, we're going to use this information to quantify the benefits or the effectiveness of our debloating schemes. In the second step, we have to know which features within these applications are more likely to be used. So for that, we map the tutorials we find on the internet for these applications to Selenium scripts so that we can replay them. And we also add a couple of other tests to increase the code coverage of these applications that I'll discuss later. At the same time that we're running these tests, on the server side, we're running a code profiler that's recording the code coverage information. So now we know which parts of the application are used. And knowing that, we can also deduce which parts are not going to be used. So we propose our debloating schemes to remove those parts. And once we debloat the applications, obviously we want to make sure we don't break the applications or introduce new errors. So we run our tests and make sure no new errors are hit. And for demonstration purposes, we also run a couple of real-world exploits against these applications to show that whenever we claim that the CVE is removed, actually the exploits also break. And in this study, we're targeting 4 popular PHP applications from different categories. First one is Magento, which is an online shopping platform, MediaWiki, PHP and WordPress. So I said in one of these steps, we find tutorials for these applications and create Selenium scripts for them. So a sample tutorial for PHP would include tasks such as logging, creating a database, creating tables, running queries, or dropping tables in databases. But obviously, these tutorials don't cover everything. So for example, some of the pages on the front of the application are not covered by these tutorials. And the users are actually likely to visit these pages. Also, from previous work, we noticed that if you only focus on keeping the functionality within the application, you're likely to remove security measures or error handlers from the application. So we want to make sure we don't remove error handlers specifically as a result of debloating. So to address that, we had to run a couple of extra tests on top of these tutorials. And the first one is a monkey test, which essentially looks like this. You inject these JavaScript libraries into your application. They will scroll the page, click on random spots, type random text into the text boxes, and submit the forms. So this will navigate to different pages and also trigger error handlers within your application. Next, we run a spider on top of our application. So it extracts the URLs in each page, submit the forms, and try to crawl in all the pages within the application, which the users are also likely to go to. And lastly, we run a vulnerability scanner on our application, and knowing that these applications are mature enough that the vulnerability scanner is not likely to find anything new, it's going to inject XSS and SQL injection payloads into the forms and trigger the error handlers that the monkey testing failed to trigger. So looking at distinct files covered by these different tests, we see that clearly different parts of the application are being touched by these tools. And we also see some interesting patterns here. For example, if you look at the monkey test for PHP and Magento, you see that it covers some distinct files. And these applications in their UI rely on JavaScript. So when you compare these two with MediaWiki and WordPress, where they do not use JavaScript in their UI for navigation as much, Spider usually covers all the files that the monkey testing could potentially cover. So now that we know which parts of the application are going to be used, we can debloat what's not used. So we propose file and function level debloating now. And file level debloating will remove a file from the application if none of its lines are ever executed. And similarly, function level debloating will remove the body of a function if it's never called. And we use placeholder in specific placeholders instead of these files and functions that will notify the admins if these parts of the application are ever executed, so that they can go and investigate if the users actually need that part of the application. We also show an error message to the user saying that this part of the application is removed. And we also stop the execution within that specific path at that point, because we don't want to enter unknown states and potentially introduce new errors. So now that we know which parts of the application are not used, we debloat the applications, and we have to measure the effectiveness. So the first metric that we introduce is the reduction in size, and we measure that in terms of reduction in logical lines of code. So looking across different applications, we see that on average, file-level debloating reduces the size of an application by 33%. And function-level debloating can increase this by a further 14%. So roughly half of the source code of these applications are removed. If you look at specific applications in our data set, we see different behaviors. So for example, WordPress is more resilient to debloating, and file-level debloating can only remove 9% of its source code, whereas for Magento, 400,000 lines of code, more than 60% of the source code is actually removed. Also, in this plot, if we look at specific versions of some of these applications, we observe a different pattern. Not only the number of lines of code has increased significantly, the debloating is also more successful in these versions. And these are the latest version of PHP MediaWiki, and Magento in our data set. And when we looked closer, we realized that these versions started using external packages in their architecture. So they started using PHP Composer to pull these packages into their application. And PHP Composer is essentially the same as NPM for Node or pip for Python. And we're going to investigate this more later. The second metric we use is the reduction in cyclomatic complexity. Looking at the numbers, we observe a similar pattern here to the reduction in terms of lines of code. And this essentially tells us that the pieces of code that we're removing from the application is as complex as the pieces that are still remaining within the application. Again, we see that WordPress its cyclomatic complexity is reduced only by 6%. And if you look closer at the source code of WordPress, you realize that the architecture is kind of different for WordPress. They use these big, fat PHP files. For example, you have post.php file that handles everything that WordPress has to do with posts. And also, in terms of extra features within WordPress, if you want to do something like report on the page view statistics, you have to install a separate plugin for that. But comparing this to Magento, you have lots and lots of smaller modules that are reused across the application. And there are lots of extra features that many of the installations are not going to be using anyway. So now that we know which parts of the application are used, we also know which parts relate to which CVEs. Our Debloating Pipeline will generate a report like this for each of these applications. So for example, we know that for CVE 2014-8959, the first line, which affects PHP version 4.0.0 and resides in the file PMA-GIS factory PHP, this file is never touched during our tests. So as a result, file and function level debloating will successfully remove this file and mitigate this vulnerability. And for example, this is not the case for the next three vulnerabilities. The actual underlying file and function was used, and debloating cannot remove them. So knowing that, we come up with a table like this. We know out of 20 CVEs mapped to the source code for PHP file-level debloating can successfully remove 20% of them, and function-level debloating can remove 60% of them. The numbers are still good for other applications. We're looking at around 40% in functional level debloating. But again, when it comes to WordPress, file level debloating cannot remove any of the vulnerabilities, and function level debloating removes only 10%. Knowing which parts of the application are vulnerable, we can also look at the types of CVEs and the effect of debloating on them. So some of the observations here are that crypto and cookie-related vulnerabilities are usually spread all across the application, and debloating cannot remove them. Similarly, CSRF vulnerabilities are only removed where the underlying feature is actually removed from the application. But comparing that to code execution vulnerabilities, we can either remove the underlying feature and make the application safer, or we can also break the exploits, which are usually written in object injection gadgets, which we look at later on. We also noticed that external packages are one of the big causes of bloat in applications. So we looked at the lines of code within applications that are contributed by external packages and compared that to the lines within the main part of the application. So for PHP we see that roughly twice the number of lines from the main application is coming from external packages. And even for MediaWiki and Magento, there is still a big part of the source code residing in external packages. But once you do the function level debloating, you see that more than 80% of the lines of external packages are removed, and still a good number of main application is debloated. So looking at this from a different angle, we see that out of 45 external packages within PHP 38 of them are totally removed as a result of debloating, meaning that they were never touched. And only 4 packages are used extensively in PHP where more than 70% of the source code was exercised. Going to MediaWiki, we see more packages being used extensively, but again, for Magento, out of 71 packages, only 2 are used by more than 70%. So now the question arises, if these packages are never used, how do they actually contribute to the attack surface? So to understand that, we have to take a look at PHP Obiect Injection attacks. So in this type of exploitation, you have an unsafe deserialization where the string that ends up in the deserialization function is controlled by the attacker. So the attacker can reuse the objects defined within the context of your application. He can control the value of the properties of those objects, but he cannot control the execution flow of the application. So he has to rely on certain functions which we call magic functions within PHP. And these functions can run automatically under certain conditions. For example, the construct of an object is automatically executed when you instantiate a new instance of that object. Or if you try to print an object, the toString function is called. So the attacker reuses objects existing within the application, controls the value of properties, and injects a certain gadget chain into the application that will end up by dropping a shell on the file system or writing to a database. So to quantify the effectiveness of debloating or removing these gadgets, we relied on PHP GGC library, which is an open source list of known gadget chains within popular PHP applications. So if you know that your target web application is vulnerable and is using Doctrine package, you can use the existing gadget chain to mount your exploit. So we see that, for example, out of 6 gadgets that we found across these applications, file debloating can successfully remove 4 of them, and function level debloating breaks all of the known gadget chains for these applications. And we also released all the source code we have and the pipeline and the artifacts for this paper. They're available at debloating.com. If you want to debloat your custom web applications, you can use our pipeline. If you want to play around with the existing debloated web applications, you can do that. Also, we have the source code coverage so that you can see how these tests exercise the application. And more importantly, the CVE mappings are available that can be used in future research. And we had to also map a couple of exploits or generate them for this paper. They're also available. So to conclude, debloating can reduce the attack surface of web applications pretty significantly. Up to 71% reduction in terms of logical lines of code is observed, up to 60% of reduction in CVEs, and up to 100% reduction in object injection gadgets. We also see that web debloating is different compared to binary debloating because web vulnerabilities and the exploitation is different here. You cannot only rely on removing that code and expect to reduce the attack surface significantly. We also need to focus more on increasing the usability and performance of these systems if we want to run them with low overhead in the production environment. And finally, make sure you visit debloating.com. So with that, I'm happy to take your questions.
We have a lot of time for questions, so please line up near the microphones.
All right. Hey, Ben from CISPA. Thanks for the talk and also for making the tool available. Can you give me an idea of why the WordPress developers would put some code into their code base, not even like third-party code, but their own code base, that they never use? Do you have any ideas on what was being removed from like the core components of, let's say, WordPress or Magento or whatever?
Right. Well, so WordPress is trying really hard to support this backward compatibility. So if you look at the source code, you frequently see multiple functions doing the same thing with different interfaces that they had to leave there not to break any, the plugins and stuff like that. So I would say one big part of it is that, because in terms of features, WordPress is not that bloated, but you can still find parts of the application that some users may not use anyway. Right?
All right, thanks.
Hi, Emily Stark from Google. I was wondering how confident you are that your coverage is comprehensive.
Right. So comparing this to different debloating schemes, here we're not aiming to have 100% code coverage, right? Because we're somehow modeling how users use the features within these applications. If we reach 100% code coverage, then essentially we're not debloating anything. But the list of tutorials is available in our paper and also on our website. And I'm pretty confident that for these target applications, the main features are still there and they're usable. But again, in the future work, we're also targeting debloating for specific use cases or for specific users, because you cannot have a model that represents all the possible users of an application.
Thanks.
All right. I'll ask a question quickly. Okay. The monkey testing, will it also test areas of the code that no one is actually using? Like it's theoretically reachable, but like, is there a way to, maybe we could look at logs or something to like in future work?
Well, yeah, it can potentially target those parts, but a part of our reasoning is that if that feature is easy to get to, then it's somehow likely for the users to trigger that. But usually applications are pretty complex, so you have to have specific values and specific forms to get those to those deep states, which the monkey is not likely to get to.
So assuming that like somebody from WordPress would be here in the audience, what would you tell them to change, either to, well, enable debloating or kind of removing legacy code? Any like suggestions?
What was the last?
So the question is like, if there's somebody from WordPress here, right, what would you tell them to either help your pipeline along or not have bloated code in the first place?
Right. Well, so one part of the suggestion would be to be more vigilant in terms of pulling external dependencies in our application. So for example, for Magento, we observed that some of the development packages are still available when you download the production zip file from the website. So you don't need code coverage or PHP unit when you're deploying a real installation of Magento. And some parts depend on how users use the app. They have to be there. They can be disabled by default, but debloating can also help.
All right. Yeah. Thanks.
Is there anyone from WordPress in the audience? So I was going to say, everyone from security will say many things to them. It's not. All right, well, let's thank the speaker again.